All right, welcome everyone. Today we're diving into something pretty amazing, differential equations. This is the hidden mathematical language that describes, well, literally everything that moves, grows, or changes in our universe. From a planet orbiting the sun to the money in your bank account, change is the one constant. And these equations, they give us the rules. So, that really gets you thinking, right? How on earth do we write down the rules for a world that's in constant motion? It seems like an impossible task. But, as always, mathematics gives us this incredibly powerful and elegant answer. Okay, so here's how we're going to tackle this. First, we'll get right to the heart of what a differential equation even is. Then, we'll make that idea real with a simple story about a falling ball. From there, we'll kind of open up the mathematician's toolbox to see the different types, and we'll see why people call them the language of the universe. And finally, we'll peek over the horizon at the mysteries that are still keeping scientists up at night. Okay, first up, the mathematics of change. Let's not waste any time. What is a differential equation? So at its core, it's an equation that connects a function with its own derivatives. And if you're a bit rusty, a derivative is just the fancy math term for a rate of change. So think of it this way. It connects how much of something there is with how fast that something is changing. That relationship, that connection, that's the magic key to modeling the world. You know, a great way to think about it is like a recipe. The equation doesn't just tell you the final result. No, it gives you the step-by-step instructions for how the system evolves over time, all based on where it is right now. It's a recipe for change itself. Okay, so that's the theory. But to really get a feel for this, we need a simple, real-world example. So let's look at a ball's simple story and actually see one of these equations in action. So just imagine you drop a ball. Seems simple, right? But its little journey to the ground is a perfect story told in the language of differential equations. We don't need some super complex formula to get started. We just need to understand the forces at play. Here's the deal. Two main forces are acting on that ball. First, you've got gravity, pulling it down with a constant force. But second, you've got air resistance pushing back up. And, this is key, that push gets stronger the faster the ball falls. The ball's acceleration, which is just the rate of change of its velocity, is the result of these two forces fighting it out. And boom, right there we have it. The ball's rate of change, its acceleration, depends on its current state, its velocity. That is a differential equation playing out in the real world. Now that we've got the basic idea down, let's see how this thing builds. See, it turns out there isn't just one type of differential equation. Not at all. Mathematicians sort them into categories to figure out how to solve them. So let's take a quick peek inside the toolbox. Okay, the first big split is between ordinary and partial differential equations. You'll hear people call them ODEs and PDEs. An ODE is pretty straightforward. It deals with a function of just one variable, like our falling ball, where its velocity only changes with respect to time. A PDE, though, is a whole other level of complexity. It handles functions of multiple variables. A perfect example is heat spreading across a metal plate. The temperature depends on both the location on the plate and the time. And the next big distinction is between linear and nonlinear. Now, linear equations are the nice, predictable ones, but nonlinear equations, well, that's where things get really wild. The relationships are way more complex, and these are the equations we use to model chaotic systems, like weather patterns or turbulence. It's where a tiny change in one place can lead to massive, unpredictable results down the line. We're talking about the mathematical source of the butterfly effect. So, we have this incredible mathematical toolbox, but so what? What's the big picture? Let's zoom out and explore why these equations are so often called the language of the universe. And this isn't some new idea, by the way. As you can see here, the story pretty much begins with the invention of calculus itself. Newton, Bernoulli, Euler, Lagrange, Fourier, these are some of the absolute giants of history, and they built this field piece by piece, discovering the mathematical rules that govern motion, mechanics, and even how heat flows. And today, oh man, their use has just exploded. Physics, biology, economics, engineering, finance, astronomy. You name a field that deals with change, and I promise you, you will find differential equations right at its heart. From modeling how a population of animals grows, to designing a stable bridge, to pricing stock options with the Black-Scholes equation, they're everywhere. And this right here is what is so mind-blowing about all of this. Just think about it for a second. The exact same mathematical structure, the wave equation, can describe light from a distant star, the sound moving through the air, and the ripples on a pond. These are completely different physical things, yet they are all united, all described by the same mathematical truth. It's just an incredibly profound, unifying principle for understanding our entire world. Now, it might seem like we've got this all figured out, but this story is not over, not by a long shot. So for our last section, let's look out at the mathematical horizon, at what is still unsolved and unexplained. So here's the fascinating truth. A lot of the time, we can write down an equation that perfectly describes a system, but we can't actually find a simple, neat formula for its solution. For many of the most complex problems out there, we have to rely on supercomputers to run simulations and just find approximate answers. And a perfect example of this is the Navier-Stokes equations. These are the PDEs that govern how fluids flow, everything from water in a pipe to the air flowing over an airplane's wing. They are absolutely essential to engineering. But their fundamental mathematical properties, we still don't fully understand them. In fact, get this. Proving certain basic things about their solutions is one of the 7 Millennium Prize problems. There is a $1 million prize waiting for whoever can crack it. And that leaves us with this final, really tantalizing thought. For centuries, we've been translating the universe's rules into these equations.